Linear regression is a fundamental statistical and machine learning technique used to understand relationships between variables. In this video, we'll break down what linear regression is, how to derive it, and how you can actually use it in a practical Python application. The problem setting for linear regression is the following. There is data y that is linearly related to x, and we want to find a function that describes this relation. However, the samples that we have from y are corrupted with noise, which makes the problem a bit trickier than just drawing a straight line through the measurements. Linear regression is a way of finding this linear relationship between x and y using a mathematical framework. In order to solve this problem, we need to define our mathematical framework. First of all, we define the linear function x using a bias term w1, which allows a constant offset on the y-axis and a constant multiplicative term w2. This becomes a data model assumption that we want to fit. Then we need a measure or metric to describe how well the fitted data actually describes the available samples. A very common way of doing this is to analyze the distance between the samples and the linear function and summing over them. In order to avoid that positive and negative errors can compensate each other, we square them before summation. This is also called the square error function, or Euclidean norm of the error vector. The goal now becomes to find the parameters w that minimize the square error. W are also called the model parameters, since they define the model or function that we fit. The function to minimize is also called the loss function. Matrix vector notation makes our lives much easier when dealing with problems such as linear regression, which is why we usually try to condense everything into such a form. We collect all samples of y into a vector and the corresponding x values into a matrix. A column filled with ones is necessary in this matrix to introduce the constant offset. This is done for all n data samples, and then by also writing the two coefficients w1 and w2 into a vector, the linear relation between data samples and their y value can be written down in a compact form. Make sure that you understand why the equations are actually equal, since these steps become crucial in the next parts. The matrix X is also often called the design matrix. Similarly, the square error can be represented by the Euclidean norm of the differences between the vector y and our model x times w. Since we want to find our model parameters w that minimize our chosen metric, the square error, this becomes an optimization problem. To solve it, we differentiate the cost function with respect to the parameters to be found and set to 0 to find the extreme value. The Euclidean norm of a vector can be rewritten as a scalar product of the vector and its transpose. Then we multiply out the terms and utilize the fact that the result will be a scalar, which makes it possible to transpose the individual terms of this sum. By doing so, we notice that the two mixed terms in the middle of the equations are actually the same and can be summarized. Then we take the derivative with respect to w, which yields the following. Finally, we can set to 0 and solve for w. The hat symbol here denotes that the solution is only an approximate estimate of the real underlying parameters that describe the data. This result is a very important one and is also called the Moore-Penrose pseudo-inverse, which is the generalization of a matrix inverse. It solves our set of overdetermined equations, which normally would lack an exact solution. Even though the mathematical derivations are very nice to look at, it is also important to see how they can be utilized in practice. Here we have an example in Python where we generate noisy samples from a linear function. Then we create a design matrix with the values of x and solve the pseudo-inverse equation. This results in parameters for w, which we can use to plot the fitted function over x. Linear regression can easily be extended to account for data which is not one, but multidimensional. It is only necessary to adapt the design matrix and the parameter vector. The bias term for the offset and the corresponding column of ones in the design matrix remains the same. Then, for each dimension in x, an additional column and its respective weight is added into the design matrix and weight vector. This procedure can be repeated indefinitely for as many dimensions as you want. How to compute the pseudo-inverse remains the same, however. Here we have an example for a two-dimensional function which depends on x1 and x2. Again, we get random samples from the function and should find the best fitting model that describes the relation between x and y. Using the pseudo-inverse approach for linear regression, the three variables in the model can be determined to describe the best fitting plane through this space. Linear regression can also be adapted to functions where the relation between x and y is nonlinear. The key to this approach is again to adapt the design matrix and keep the influence of the weights linear. Again, there is a constant offset term with the columns of ones. Then a nonlinear function is used to transform x. This can be repeated for an arbitrary number of functions depending on y. What is important here is that the functions are nonlinear in x, but the overall model is still linear in w. Then the previous approach can still be applied. An example for a nonlinear function to be fitted could be the exponential function. Here we have a constant offset, a linear term, and an exponential term, for which we get noisy data. With the same procedure as before, it is possible to determine the weights w, such that we can fit a function through the samples in an optimal fashion. Now it is time to do some practical work using linear regression. For the first exercise, you should practice on a sampled dataset. Analyze it and find a relation between x and y. Is it linear? How would you model it? Use the pseudo-inverse approach for linear regression and compare the results to the data. In the second exercise, you should think more about the design matrix. We have seen that the extensions to the linear regression model could be done for multidimensional and nonlinear problems. Is it possible to fit a nonlinear function to a multidimensional problem? If yes, then you should think of an example and generate random samples to which you fit your model. The third exercise is a more theoretical one. To find a pseudo-inverse, we solved a minimization problem. Was it actually a minimum that we found, or did we accidentally maximize the error? Thanks for watching this video about linear regression, and I hope you have fun with the exercises. Feel free to discuss your results in the comment section and also share your insights.